In this video, I will be going through the current and potential different rules for a series circuit, and then I'll go through their mathematical derivations. I'm going to start off by drawing a simple series circuit with two resistors. This has resistance R1, this has resistance R2. If you recall from my first video, the longest terminal is positive, the shortest terminal is negative. Conventional current flows from the positive to the negative terminal, so we'll have the total current going this way. Our first rule is that current is the same through components in series. This means that R1 has a current IT and R2 also has the same current IT. Then mathematically we can say that the total current is equal to the current flowing through resistor 1, which is equal to the current flowing through resistor 2. And this is only in series. And we'll call this equation 3. Our next rule is that potential difference is shared proportionally across components. So if you'd like to better understand why this is the case, I recommend you go back to my previous video. So this means that R1 has its own potential difference V1 and R2 has its own potential difference V2. Mathematically, we can say that the total potential difference supplied by the battery is equal to the potential difference across resistor 1 plus the potential difference across resistor 2. And this is in series. Now we're going to come back and use these formulas a lot in later videos. I'm going to go through the mathematical derivation of why potential difference is shared proportionally in series. Now, going back to rule number 2, if you recall from video 1, potential difference is the energy per unit charge. So it won't be a surprise that rule number 2 is due to the conservation of energy. Now this is a really key point for exams, so we're going to take it down. 2 is a consequence of the conservation of energy. And this is our key point, conservation of energy. So I'm going to draw a series circuit to help explain this. We're going to draw 3 resistors. The total potential difference supplied by the cell, we'll just call VT for now, V total. Then we have resistor 1, resistor 2, resistor 3, each with their own potential difference, V1, V2, V3. If you recall from my previous video, the longest terminal is positive, the shortest terminal is negative. So conventional current flows from positive to negative, so that's our total current. But in series, we know that the total current is the same through components. So each component will have a current IT. Now, if you recall the conservation of energy, this means that the total energy before, we'll call that ET, must be equal to the total energy after. So it must be equal to the energy required to move through V1 plus the energy required to move through resistor 2 plus the energy required to move through resistor 3. Now we can divide both sides by a constant Q, and we can do this because Q is just a number. Then you recall that potential difference is energy per unit charge. Now we can replace each of these terms with the corresponding value of V. So we get that VT is equal to V1 plus V2 plus V3, which shows us that the potential difference will split across components in series. In my next video, I'll go through the same rules but for parallel circuits.